So if we want to be able to detect clusters, the first thing we need to do is to figure out how do we define a good cluster? How do we define a good community in the graph structure point of view? So the way we think about this is the following. Our input is a graph, right? A graph on a set of vertices V, these are the circles, and a set of edges or connections E. And in our case, these connections, these lines, are simply undirected, unweighted lines, right? And what we would want to do is we can define what is called a graph partitioning task, where the idea is that we want to divide the vertices of our network into two sets, into sets A and B, in such a way that we will identify clusters. So the question is, how do we define what is a good cluster in the network? The way to think about how do we define a good cluster, I have already implicitly spoken about it, right? So kind of intuitively what we want is to say, what makes a good cluster? What makes a good cluster is to maximize the number of within cluster connections, right? So nodes that are in the same cluster, we want them to link to each other. And then we want to minimize the number of connections that go between clusters, right? So we would like to say, if this set of nodes, let's call it A, is a cluster, we want lots of connections between the members of the cluster, and we want few connections to the rest of the network, right? So we want this cluster to be kind of, in an easy way, separated from the rest of the network, right? So this is our set B in this case. So for now, we have a very simple task. We want to take our graph, split it into two pieces, where the piece that we are splitting away has lots of edges between the members of the piece and few connections to the rest of the network. So this way, we now arrive to the first definition of today's module, which we will talk about graph cuts, right? So the idea is that we want to express this cluster quality as a function of what is called the edge cut of the cluster, right? So the idea is that cut is a set of edges with only one endpoint in the cluster. So simply, if I say, what is the cut of a set A? This is simply a summation over all the edges where one endpoint of an edge is in the set A and the other endpoint is in the outside the set A. And I'm summing up together the weights of those edges, right? In our case, we assume that every weight of the edge is 1. So all this is doing is basically counting how many edges are pointing outside the set A. So, for example, if I have this graph here on 6 nodes, and if I think of set A to be this yellow set, then what is the cut score, or what is the cut of this set A? The cut of the set A is 2. Why is that? Because there are two edges, the first black edge and the second black edge, that point outside the set A, right? So one endpoint is in the set, and the other endpoint is outside the set, right? Node number 1 is in the set, and node number 5 is outside. And we have two such edges. So the cut score equals 2. So one option, we already know, for example, based on this, how we would go and identify clusters. The idea would be that I go and find sets of nodes such that are kind of very easy to be cut, right? That their cut score is small, which means I have to cut a small number of edges to separate this set from the rest of the network. The problem, however, with this is that if I use this cut score to find good clusters, I can find kind of uninteresting degenerate solutions. So the problem with the cut score is that it only kind of considers the edges pointing outside the cluster and not the edges inside the cluster. Here's an example, right? I have this graph with where intuitively we think that there are two clusters. There is a cluster of red set of nodes, and there is a cluster of kind of the green set of nodes. And what we would like to do is that we would say, oh, the best cut, the optimal cut in this network in some sense is cutting here along the blue line. But for example, if we say, what is the cut in this network that optimizes the cut score, that basically gives us the lowest possible cut score, would be cutting here, right? Would be cutting this lonely green node away from the network, because all we need to do to separate this node out is to cut a single edge. What we would like to do intuitively, we would like to cut here where the blue line goes, right? Because we are cutting two edges and kind of nicely split the graph into two pieces. So the question is, how should we modify our cut score definition such that, in some sense, the optimal cut we will find is here in the middle of the graph? The way we do the modification is to realize what are the problems. There are two problems with the cut score. First one is that it only considers kind of external connections to the cluster, only kind of edges pointing outside the cluster. And it doesn't consider internal connections, right? Connections between the members of the cluster. So a fix that helps here is a metric called conductance, right? So conductance is a way to incorporate the connectivity of the group to the rest of the network relative to the internal connectivity of a given group. So the way we will do this is the following. We will define a notion of conductance of a given set A. We denote conductance with a Greek letter phi. And conductance is very simple. All it is doing is to saying, first we count the number of edges where one endpoint is in the set A and the other endpoint is outside the set A. This is nothing else than the cut of the set A, right? We have already defined this. But now we divide the cut by what is called the volume, right? We divide the cut by the volume of set A. And how do we define the volume? Volume is simply the total weight of the edges with at least one endpoint in the set A. In other words, volume is simply the sum of the degrees of all the nodes that are in the set A. And a degree of a node is simply the number of connections adjacent to a given node, right? So intuitively what we are doing is we are taking the number of edges that point outside the cluster, this is the cut, and then we divide this by the number of edges that are in some sense inside the cluster plus the edges that point outside, right? And the lower this ratio, the lower the phi, the better the cluster we have found. One thing that deserves to be said here is that we have this minimum here, and the idea is that we can think about the set A to be less than half of the size of the graph, right? So the idea is if I have set A to be very big, then the volume of A can kind of overpower the whole thing. So the good thing to think about is that the size of set A is less than the number of vertices divided by 2. And then the 2m minus volume of A kind of never takes over. So that's basically the idea. And why would we want to use this criterion is because it produces more balanced partitions. In some sense, it produces pieces, clusters that are kind of comparable sizes. To give you an example, here I have a graph with the blue nodes. And imagine that the red nodes are what I call set A. And now I can ask, what is the conductance of this set A? And in the first case, I have two nodes. What is the cut score? I'm cutting two edges, right? I cut an edge here and I cut an edge there, so I get 2. What is the sum of the degrees? I have the first node has degree 1, the second node has degree 3, so the sum of the degrees is 4, so 2 over 4 equals 0.5, right? So conductance of the set A on the left-hand side example is 1/2. For example, if I think of set A in the example of the right to be the cut that goes through the red line, then if I do the counting, it turns out I have to cut 6 edges. And what is the sum of the degrees of the nodes that are inside the set A? It turns out to be 92. So 6 over 92 is 0.065, right? So in some sense, the conductance score of the set A on the right is 10 times better or 10 times lower than conductance score of the set on the left. So this means that that on the right-hand side, we found a 10 times better cluster than on the left-hand side.